Hello, this is the group project for SEMM 2613 Material Science Section 9, and we are from Group 2 with the copper aluminium alloy. Our group member consists of 4 members, which is me, Hakim Afifi, Hridoy Mahe, Jacob Basil, and Johnny Chiang. Aluminium-based and aluminum alloy-based material matrix composite have been widely used in automobile and aerospace industry. Many of these product reinforcements are generated using mixed reaction procedures, and the reinforcements obtained are usually thermodynamically stable. This approach also enhances the interfacial interaction between reinforcement and matrix. Aluminum copper are one of the products which intermetallic compounds are formed during the reaction, and these intermetallics act as secondary phase reinforcement to the matrix. Copper was chosen since it's one of the few elements with high solubility in aluminum. Thus, the sintered aluminum copper product has an aluminum copper solid solution matrix that is mechanically tougher than a pure aluminum matrix. Our objectives are to investigate the phase diagram, solidification process, and microstructure of different types of alloy category. The method of improving material properties also will be discussed.
I'm Johnny. For question 2, discuss on the phase diagram. The eutectic alloy in the CuAl phase diagram having the composition of 32.7% of copper, and the isothermal reaction is also happen at this eutectic point, where the alloy solidify at a constant temperature of 548.2 degrees Celsius. And the composition that are less than the eutectic alloy is considered as a hypoeutectic alloy, and the alloy that are more than the eutectic alloy is considered as a hypereutectic alloy. The intermetallic compound is the chemical compound consisting of 2 or more metals. In this case, the intermetallic compound is at the theta phase, which is CuAl2. The composition that I choose for question 2 is eutectic alloy, which consists of 32.7% of copper. The phase diagram is shown in the slides. At point 1, the temperature is 900 degrees Celsius, and at point 2, which is also known as eutectic point, is 548.2 degrees Celsius. At point 3, the temperature is 400 degrees Celsius. At point 1, the alloy behaves like a pure metal at 900 degrees Celsius in liquid form, which can be shown in the microstructure 1. As the heat is being removed from the system for liquid to cool down until point 2, which is 548.2 degrees Celsius, which is also known as eutectic point, the alloy will start to solidify, and the nuclide will start to nucleate, as shown in microstructure 2. And after the whole volume solidify at a constant temperature of 548.2 degrees Celsius, the temperature will drop further to the room temperature. And this constant temperature reaction is called as isothermal solidifications. At point 3, which is 400 degrees Celsius, 2 solid solutions will start to form straight away in one solidification reaction, which is homogeneous phase K phase, kappa solid, and also theta phase, which is the intermetallic copper aluminite, which is CuAl2. For composition and the amount of phases, I choose at 400 degrees Celsius. So by using the timeline method, by drawing a line to the left and to the right, we can find the composition of kappa solid consists of 3% of copper, while the composition of theta consists of 53% of copper. For the phase fraction of the kappa solid, we can determine by using the formula B over A minus B times 100%. If you want to find the kappa solid, the distance that you choose is always opposite, which is B. So the distance of the B can be determined by 53% minus 32.7%, and A can be determined by 32.7% minus 3%. So the final answer for phase fraction of kappa solid is 40.6%. Hence, the phase fraction for the theta phase is 100 minus 40.6%, which is 59.4%, because the total is 100%. For the second composition that I choose for question 2 is a hypoeutectic copper aluminium alloy, which consists of 20% of copper. Compared with the eutectic points, this phase diagram has 4 points to be stated. So for point 1, the temperature is 900 degrees Celsius, and point 2, which touches the liquidness line, is 610 degrees Celsius, and point 3 is 548.2 degrees Celsius, and lastly is 400 degrees Celsius. Same as before, at point 1, the alloy behaves like a pure metal at 900 degrees Celsius in liquid form, which can be shown in microstructure 1. As the temperature is dropped further to 610, which is point 2, and it also touches the liquidness line, solidification process will begin. Only alpha solid solution will solidify at around 3% of copper, and the remaining liquid contains 80% of aluminium and 20% of copper. The composition can be determined by using the timeline method. As the temperature is dropped further to 580 degrees Celsius, the nucleus will continue to grow bigger and bigger within this two-phase region, and its composition of alpha has increased to 4% rather than 3% just now. Then the alpha solid solution will stop to solidify at point 3, which is 548 degrees Celsius, and there are some remaining liquid left in the whole volume which having the same composition with the eutectic points, and the alpha solid solution that solidified before is also in this microstructure 3. So at point 4, the remaining liquid will start to transform into a laminar structure which consists of eutectic alpha and theta. For composition and the amount of phases, I choose at 580 degrees Celsius. The composition is also determined by using the timeline method. The composition of the copper solid is around 4% of copper, while the composition of remaining liquid is at around 28% of copper. Different from eutectic alloy, the composition on the right hand side touches the liquidness line instead of the theta phase. And the phase fraction of the copper solid is using the same method to determine, which is B over A minus B times 100%. And the final answer is 33.33%. Hence, the phase fraction for the liquid is equal to 100% minus 33.33% equal to 66.67%.
Hello, it's me again, Hakim. For the first alloy, I choose the aluminum copper alloy with 70% of weight percentage of copper, and this alloy belongs to the hypoeutectic category. For solidification process, the solidification starts at 1000 degrees Celsius, and the alloy is still in the liquid form. Next, at the 310 degrees Celsius, the primary alpha starts to form. Move on to the 580 degrees Celsius, the primary alpha gets bigger and the composition of the liquid is reaching the eutectic composition. At the 545 degrees Celsius, the remaining liquid will be transformed into two solids simultaneously and form the eutectic composition. And lastly, the cooling process will end at the 400 degrees Celsius, where the alloy remains in form of alpha and beta. Moving on to the microstructure sketch. The sketching is taken at the temperature 1610, 545 and 400 degrees Celsius. As you can see in the sketch, the alpha started to form at 310 degrees Celsius. For the cooling curve of the cooling process, the process initially took place at 1000 degrees Celsius until 610 degrees Celsius. At this point, the alpha solid solution began. Then it is further cooled until 545 degrees Celsius. At this point, the alpha solid solution ends. For the hypoeutectic alloy, I choose the aluminum copper with the 50% of weight percentage of copper. And the solidification process began at 1000 degrees Celsius. At this point, the solid solution is still in the liquid form. Then, at the 590 degrees Celsius, the primary beta started to form. After that, at the 580 degree, the primary beta gets bigger and the composition of the liquid reaching the eutectic composition. Finally, at 545 degrees Celsius, the remaining liquid will be transformed into two solids simultaneously and form the eutectic composition. The microstructure sketch for hypoeutectic taken at temperature 1000, 519, 545 and 400 degrees Celsius. As we can see in the sketch, the beta started to form at 590 degrees Celsius, and for the cooling curve, The process began at 1000 degrees Celsius and continued at 590 degrees Celsius, at which point the beta solid solution began. This beta solid solution is then cooled further until reach 545 degrees, which is the solid solution will be end at this point. For the hyper-eutatic phase composition, I also use temperature at 580 degrees Celsius. At this temperature, the phase fraction for liquid is 28.57%, while beta is 71.43%, and the copper composition in the liquid is 14%, while beta is 0.5%.
Hey guys, my name is Jacob, and the composition that I've chosen today is the hypoeutatic copper aluminium alloy with 10% weightage of copper. So as you can see from the phase diagram shown in this slide, there are four temperature phases in which I have chosen. At point 1, which is 800 degrees Celsius, at point 2, 640 degrees Celsius, which lie on the equidus line, and point 3, it's 548.2 degrees Celsius, which lie on the eutatic point temperature. At point 4, it is 400 degrees Celsius. And in this slide, the microstructure of the alloy can be seen with respect to their temperatures. So at 800 degrees Celsius, the alloy is in full liquid form, and then as it cools down, the primary alpha starts to form as it crosses the liquidus line, which is at 640 degrees Celsius. As the alloy cools further, the primary alpha enlarges and lamella begins to formulate at around approximately 580 degrees Celsius, and the alpha solids would stop forming at around 548.2 degrees Celsius, which is the eutatic point temperature. So the temperature cools even further at 400 degrees Celsius, and at that point, the remaining liquid transforms into alpha solids and beta solids simultaneously. And as we can see from the cooling curve of the cooling curve graph on the right side here, it shows the chronological stage in which the alloy goes on when it cools. In this slide, it shows the phase fraction at the temperature at 580 degrees Celsius. So the liquid column and the alpha column shows the calculation for the mass fraction for its liquid section and the mass fraction for its alpha solid formulation. So the formula for calculating the mass fraction for liquid can be used given A divided by A plus B times 100%. A value, which is can be seen from the phase diagram graph, is the range between the yellow line and the A point, and B can be seen as the range between the yellow line and to the point B, which touches the liquidus line. And at A point is the solidus line, sorry. And so the mass fraction for liquid is given 30%, and the mass fraction for the alpha solids is given by the formula of B over A plus B times 100%, which gives 70%. And the composition of copper in liquid form is given by 24% copper, and the rest, which is 76% of aluminium, with the alpha solid composition of copper is at 4%, and the rest of it is aluminium. For the second composition that I have chosen is the hypereutatic copper aluminium alloy with 95 weight percentage of copper. From this phase diagram, I have chosen 3 points of temperatures. At point 1 is 1090 degrees Celsius, at point 2, 1070 degrees Celsius, and at point 3 is 1040 degrees Celsius. In this slide, we can see the microstructure of the alloy with respect to its temperatures. So at 1090 degrees Celsius, the alloy is seen to be at complete liquid form, and when the liquid cools down at around 1080 degrees Celsius, where it crosses the liquidus line, primary alpha would start to form, and as it cools even further, the primary alpha would enlarge at a great rate. Due to the high composition of copper inside this alloy, the solidification process for the alpha solids takes place really quick thanks to its high melting point properties. In this table, we can see that the phase fraction that I have chosen is at 1070 degrees Celsius. So the mass fraction for liquid can use the formula as before, which is A over A plus B times 100%, which gives us 50%, followed by its mass of alpha solid fraction, which is 50% as well. So the composition of copper for its liquid phase is at 94% with 6% of aluminium, and its alpha solid composition of copper is at 96% with 4% of aluminium.
This is the phase diagram of a copper aluminium alloy. Aluminium bronze is a form of bronze where copper is added to the aluminium. Here aluminium is the main alloying metal. In the phase diagram, the sky blue area shows the liquid phase of the alloy. My selected hypoeutectic copper aluminium alloy consists of 15% copper and 85% aluminium. If we observe the solidification process of the hypoeutectic alloy, we can see that for 15% copper and 85% aluminium, the alloy will still be in the liquid form at 900 degrees Celsius. However, when it comes down to 620 degrees Celsius, the primary alpha starts to form. At 580 degrees Celsius, primary alpha gets bigger and the composition of the liquid starts reaching the eutectic composition. Finally, at 545 degrees Celsius, the remaining liquid will transform into a solid state and form an eutectic composition. For better understanding of the solidification process, we draw a cooling curve of temperature versus time. Phase fraction at 580 degrees Celsius has been measured, which is 50-50, and the composition of copper is 24% and 4% accordingly. And according to the microstructure, at 900 degrees Celsius, there is still liquid. As you can see, no alpha structure is being formed, and at 620 degrees Celsius, it's being formed little by little. 545 degrees Celsius. And finally at 400 degrees Celsius it is fully formed. The selected hyper-eutectic copper aluminium alloy has 45% copper and 55% aluminium. And from the bar, as you can see, on the right side the distance is 9, and on the left side the distance is 5. For the solidification process, the alloy will still be in the liquid form at 900 degrees Celsius. The primary beta will start to form at 585 degrees Celsius. And at 580 degrees Celsius, primary beta will get bigger and the composition of the liquid will start to reach the eutectic composition. Gradually, and finally at 545 degrees Celsius, the remaining liquid will transform into a solid state and form an eutectic composition. And it has been shown clearly in the cooling curve. The distance we got from the phase diagram we can use now to determine the phase fraction of 580 degrees Celsius. And then we get the composition of copper, and the microstructure also gives a clear visualization of the solidification process at 900 degrees Celsius, 525, 580 and 545 degrees Celsius.
Hi, I'm Johnny. For question 3, method of improving material properties for copper aluminum alloy is through cold spray and nickel interlayer on the copper surface, so that the friction stir butt welded joint of aluminum copper and also the process of metallurgical could be enhanced. Before applying the friction stir butt welded joint of aluminum alloy to copper, nickel is being cold spray on the copper surface to form an interlayer. The intermetallic IMCS compound that form a single Al3 nickel 2 layer with a thickness of approximately 200 nanometer rather than approximately 0.6 micrometer without addition of nickel at the intersurface of Al2Cu and also Al4Cu9. IMCS formation is a key factor which limits the strength of the dissimilar friction stir welded joints. The average tensile strength of the joint is improved from 152 MPa to 190 MPa. Besides, the ductility of the joint has a significant increase from approximately 5.5% to approximately 10.5%. Step 1. The aluminium alloy and also the pure copper plate were friction stir welded using a modified molding machine in a butt weld configurations. For step 2, the side surface of the copper plate was polished and washed with the ethanol before applying welding, and then nickel coating will be cold sprayed as schematically illustrated in figure 2a. For step 3, the coating process was performed in a parallel passes through the length of the copper plates, and the aluminum alloy was placed on the advancing sides with two offsets of 0.8 mm into the aluminum sides, and the friction stir welding setup is illustrated as figure 2b. Step 4. The dimension and also the sectioning location of the tensile coupon were schematically illustrated in figure 2c. Step 5. The metallographic specimens were mounted following standard grinding and polishing procedures with final polishing. Microstructure examination of the metallographic specimens was performed using an optical microscope and also a scanning electron microscope. Last step, before the tensile testing, the tensile coupons were grounded using an abrasive paper to remove the rust surface that produced during the water jet cutting process. For application of material, aluminum alloy offer low density along with excellent electrical and thermal conductivities. Therefore, structure incorporating aluminum copper joints may substitute for components which make the entire of copper achieve cost and weight reduction, which creating demand for aluminum copper joints in a wide variety of industrial applications such as electrical connector, refrigeration tubes, heat exchangers tubes, bus bar, and also foil conductor in transformer.
Aluminium bronze is a form of bronze in which aluminium is added to copper. Here the aluminium is the major alloying metal. Aluminum bronzes are frequently employed in areas where their corrosion resistance makes them a better choice than other engineering materials. And this is the main reason why we use aluminum bronzes, because of their corrosion resistance. For their applications, they have plain bearings, landing gears, components on airplanes, guitar strings, valve components, engine components, underwater fastening in naval architecture, ship propellers, and jewelry. All of these have the application of aluminum bronze. The method of improving the material properties of aluminum bronze is, there's one way to do it is cold spraying nickel on the copper surface to form an interlayer. And for the intermetallic compounds of the aluminum bronze, we have C